the original formulation of Maldacena 25.5 years ago. So the formulation, the original formulation was for string theory in the background of AdS-5, anti-de Sitter 5-dimensional times of 5 sphere, versus n equal 4 super M mills with the SUN gauge group, which, as we saw, was the low energy theory on the world volume of ND3 brains, where the field theory is living at the boundary of AdS-5 times S5, and the equality is in a certain limit that we will describe. So I will describe for you the so-called heuristical derivation of Maldacena, which means we sort of understand more or less what the theories involved are, but not the details of the derivation or any relation beyond a simple relation between theories. So we will not derive any specific map between observables at this point. So the heuristic derivation is based on this fundamental equality of Polchinski that we described between D brains, defined as abstract objects in string theory, the endpoints of strings, and extremal P brains, which are solutions of supergravity, the low energy limit of string theory. As solutions of supergravity, so as extremal P brains, these curve space. So the solution is written here again. So it's the metric is the harmonic function to -1/2 times the directions parallel to the brain plus the harmonic function to +1/2 times the directions perpendicular to the brain. The harmonic function is this one with a plus sign. And the radius R that appears in here is 4 pi G string alpha prime, sorry, R to the 4 is 4 pi alpha prime squared and N. Yeah, the relation is written wrongly here. It's R to the 4 is equal to this. Now, the derivation is based on the idea that we can add a small perturbation, a small mass perturbation around the extremal solution. So the extremal solution was for mass rather equal to the charge, right, QP. I just add a small delta M, which means I go slightly away from extremality. When I do this, I create a horizon. So technically, this solution also has a horizon, but only at R equal to 0. So R equal to 0 is in here both singularity and horizon. So it's an extremal case. And if I add a small mass, then the singularity stays at R equal to 0, but I evolve and it appears in a horizon at a positive radius. So because I have an horizon, as Hawking taught us, we have Hawking radiation. A black hole radiates thermally. And there's a way to understand this Hawking radiation. So Hawking radiation. So for p branes becomes, in string theory, a phenomenon where I have two strings on the D brane. So I have a D3 brane and two open strings that end on it that go towards each other, and at some point they collide. And when they collide, they join endpoints. And now the closed string can move away from the D brane into the bulk, which means we have a sort of radiation, right? So the Hawking radiation is used in string theory, that the collision of two open strings, which are excitations modes of the D brane, and the formation of a closed string, which is a mode that propagates into the bulk. All right, so as we said, the derivation is based on this, on the basic equality of Polchinski between D branes and P branes. And correspondingly, we have 2 points of view on this phenomenon. So the point of view number 1, when we think of D branes, so the endpoints of strings. So let's say point of view number 1. We have what? We have the open strings in this picture, the open strings, and at low energies, low energy means alpha prime goes to 0. We've seen that gives n equal 4 spam mills. Okay, we've seen that. Then the other ingredient are the closed strings into bulk. Right? And what do those represent? Well, the closed strings, at least in the alpha prime goes to 0 limit. So in this limit, alpha prime goes to 0, which is a low energy limit. In this low energy limit, we said string theory becomes supergravity. Okay, we have supergravity. And then we have the interactions between them. Interactions described by this diagram. All right? Okay. So we said the bulk action becomes supergravity action. The brane action becomes n equal 4 super Mills action. How about the interactions? Well, so the interactions have to be proportional to the Newton coupling, kappa Newton, for gravitational interaction. I can figure out that this is proportional to G string alpha prime squared. So in front of gravitational action, we have 1 over kappa Newton squared, and this would be 1 over G string squared alpha prime fourth. 1 over G string squared is normal, what you expect in front of an action. And this 1 over alpha prime to the fourth is because of dimensional reasons. 1 over alpha prime to the fourth has dimension 4. So together with the 2 dimensions, to the dimension 2 reaches scalar, that gives the dimension 10 of a Lagrangian in 10 dimensions. But then alpha prime goes to 0, so the interactions go to 0. So the interactions go to 0, but more precisely, the self-interaction of gravity defined by kappa Newton also goes to 0. So we have free gravity. Okay, non-interacting gravity. Okay, so an observation of, so as we said, we have then free gravity in the bulk, n equal 4 spam-mills on the D3 branes. And the observation is that the boundary of the 10-dimensional space AdS-5 cross S5 is 4-dimensional. It's either R31 or R tau cross S3, depending on whether we look at the Poincaré patch or the global coordinates. But importantly, there's no S5. So the point is, if you do all the transformations we did for the Penrose diagram, so you take out some conformal factors. When you do that, you notice that the thing multiplying the metric on S5 goes to 0. So this shrinks to a point, and so the boundary of this space is 4-dimensional. Point of view number 2. So point of view number 2 is as a solution of supergravity. So we've seen the supergravity solution, but for the p-branes, but now we need to consider the alpha prime goes to 0 limit. And moreover, we have to consider 2 asymptotic limits. So the solution has 2 asymptotic limits. R going to 0 and R goes to infinity. But now, so R goes to infinity, this was Minkowski space. So away from the D brane, from the D3 brane, the space is flat. That's kind of standard. But R going to 0, we will see in more detail, but we could just state it at this moment. It's AdS-5 cross S5. Now, to understand the limit, we have to consider the energy at a certain point. So let me consider the point defined by R. And so the energy corresponds to time translations. And so the energy at the point R is defined by the derivative with respect to the proper time, which is 1 over square root minus G00, and then the derivative with respect to coordinate time. But this one is what we will find at what we will measure at infinity, where the metric is flat. So we get a relation between the energy at infinity, that the energy at infinity is square root minus G00, which it's h to minus 1/4 ER. And now further, so h was this. Now further, I consider the limit where R goes to 0, and therefore I can ignore the 1. And so h to minus 1/4 is just R. So this goes like R ER. So then, if I fix the energy at point R, then the energy at infinity goes to 0. So if this is fixed, then this goes to 0. And energy goes to 0 means low energy. Okay. And on the other hand, so this was the analysis for R goes to 0. Now the analysis for R goes to infinity at large distances. Large distances means also large lengths. So delta R goes also to infinity. And delta R goes to infinity means, you know, large scales or low energies, right? So this means E goes to 0. And the effective gravity coupling, so the gravitational coupling G Newton, has dimension -2. So then in order to, I should say -2 in 2 dimensions. So in 2 dimensions, I would write times E squared, but in general, I write times D -2. Either way, we see that this goes to 0. So this is the effective coupling. Effective meaning effective coupling has to be something that's dimensionless, right? So, so out of the dimensional coupling G Newton, you find the effective coupling that goes to 0. So at large distances, you find free gravity. Okay, so at large distances, we have free gravity. And now we compare the 2 points of view, right? So we've seen that the bulk, so this was bulk, and here we had free gravity in the bulk. And here we have also free gravity at large distances. So these 2 things are the same, right? Remember, intersections goes to 0, so here we have just free gravity. And so we're left with what? We're left with, on one side, n equal 4 super Yang-Mills, and on the other side, AdS-5 cross S5. Okay? So that's basically it. We have written point of view number 1, which was D branes. Point of view number 2, which was P branes, due to Polchinski. And we have shown what we have in this low energy limit. And by seeing that we have the same free gravity at infinity, the rest has to be also the same. And the rest is, on one side, n equal 4 super Yang-Mills, on the other side, AdS-5 cross S5. Then the details have to be understood also. So n equal 4 super Yang-Mills is with gauge group SUN. So here comes, there was a question before, so the 3 branes would correspond to the group UN, but the U1 part is a center of mass motion that is not understood in this, not relevant to this mapping. So we are left with the SUN. Yeah, there's a question. Is there no worry about? No, the point is we're looking at E goes to 0, so the coupling goes to 0. So the coupling becomes irrelevant, which means that there are no interactions, so I ignore them. Now, of course, at other energies, this is important, but the point is we're interested in low energies, so this goes to 0, so it doesn't matter. Yes, another question. Okay, so let me repeat the question. So the question was how solid was the argument, being that the argument was based on Polchinski's paper, which relates D branes with P branes by relating their masses and charges. That's what I said, which you said it looks indirect. But the point is that you are in the same theory. So supergravity is viewed as the low energy part of string theory. So we are in the same theory, and we're seeing objects with the same masses and charges. Well, if you're an experimentalist and you see the same masses and charges, you know, it's the same particle, right? So that's really it. It's nothing indirect. It's just... Sure, different energy regimes, but the point is this is a non-perturbative object, right? So it's not, yeah, there's nothing different about this object, right? Okay. Or, yes, another question. Right, so let me go to that. So the background for this, the string theory, as we said, is R going to 0. And if we just take R going to 0 for this background, excuse me, so HP minus a half dx parallel squared plus HP plus a half dx perpendicular squared. If we just take the limit R going to 0 of this, HP, as we said, goes to R4 over R4. And the background becomes just this R squared, x0 squared, dx parallel squared plus dx0 squared, plus R squared d omega 5 squared. So this is AdS-5 here, and here it's S5. Okay, so then you ask, where do the brane live? Well, let's look at where this was originally, right? So the P branes lived at R equal to 0, right? And then we took the limit, further we took the limit R going to 0, right? And we obtained AdS-5 cross S5. So the space AdS-5 cross S5 was very close to the D branes, right? And then it remains to define where is the where in AdS-5 correspond the D branes. And really, if you look in here, this space has no more singularity. This space had a singularity, right? So there's no more singularity. And so the only, you cannot say that the center corresponds to the D branes or something like that. The only place where this can happen is the boundary, r going to infinity, or x0 goes to 0. So the d-branes, and therefore n equal 4 super mils, lives at the boundary. Now, I should qualify that statement a little bit, because, so if we're talking about a conformal field theory like n equal 4 super mils, that's correct. Otherwise, if the theory is slightly non-conformal, which means the energy, it depends, which means the things at different energy scales are different, then we will see that it's better to think that the coordinate r, which will be related to energy, represents the energy scale of the field theory. So from that point of view, if you're talking about a non-conformal theory, it's better to think as the theory being probing various energy regimes according to the radius. But in a conformal theory, we can safely say that we have the field theory at the boundary. So now, let's define a little bit the limit a little bit better. So, as we said, for r going to 0, we had the harmonic function is r to the 4 divided by the radius to the 4. But this r to the 4 contains alpha prime squared. So that means that h goes like alpha prime squared over r4. Okay? And now let's consider, so we looked in here at the relation between the energy at infinity and the energy at point r. However, let's consider that we keep the energy at point r not fixed in itself, since that is also part of a limit. We're taking r to 0. But rather, we keep fixed the energy with respect to the string scale, which is a dimensionless quantity. So now let me say I keep fixed ER times square root alpha prime. Okay? And then I write E at infinity in terms of ER square root alpha prime. And so ER, E at infinity was R times ER. So this is R. Sorry. So this is RER. ER cancels over square root alpha prime. Wait, I'm doing something wrong here. What am I doing wrong? No, yeah. Sorry. So yeah, this was not correct. So it's h to minus 1/4 is r divided by square root alpha prime. So before I neglected it, right? So h to minus 1/4 is r over square root alpha prime. So so this becomes, so this ratio becomes just r over alpha prime. So now, if this is fixed, that means I have fixed the ratio of r to alpha prime when both goes to 0, right? So R goes to 0 was the limit needed to obtain AdS-5, and alpha prime goes to 0 is the limit needed to have low energy. And in that limit, we keep fixed their ratio. And the interpretation is, on one hand, I keep fixed the energy at infinity, which is the energy in field theory. And on the other hand, I keep fixed the energy at point R in string units. Okay. All right. So if I do this, then the metric becomes as written on page 68. So there's an overall alpha prime that goes to 0, but otherwise the things in the square brackets are all finite quantities. Okay. So we've taken, another point is, we've taken alpha prime goes to 0. So we have alpha prime goes to 0, which means, so alpha prime governs, it's what appears in front of the string world sheet action. So it governs world sheet corrections, string world sheet corrections. But in string theory, I have also the coupling of strings, which amounts to just an interaction of two strings colliding and getting into another one. And so if I want to, excuse me, if I want to have small string corrections, I need to put G string to 0 as well, because only in that limit string theory reduces to supergravity, when I don't have quantum corrections. So I have the limit involves alpha prime to 0 and G string goes to 0. And then R squared, yeah, again, this is actually an error. This is actually R squared over alpha prime is square root 4 pi GSN. And this has to be then fixed and large. So this is fixed in the, because this goes to 0. But then this is the radius of both AdS-5 and S5. And so I want this radius to be large enough, because if the space has a small radius, if like a sphere has a small radius, then obviously I will get corrections due to the curvature. So that is not good. So I need this to be fixed but large. What that means is an order of limits, right? We first take alpha prime to 0, and then we have this GSN that needs to be large. Remembering that in this limit, GS goes to 0, which means that also n has to go to infinity. Okay. So n goes to infinity, the large n limit. Well, the large n limit was considered by 't Hooft for gauge theories. And so the large n 't Hooft limit so he considered this large n limit and considered theories with both theories like QCD with both a joint and a fundamental indices. But for us, we're limiting ourselves with theories with only adjoints, because that's the case of n equal 4 super Yang-Mills. And then his analysis, it's a very short paper, like 4 pages or something at most. You should read it. It's very good. And then the amplitude for a Feynman diagram. Examples of Feynman diagrams are given there on page 69. So this goes like G squared n to a number, namely the number of loops, times n to 1 minus twice the number of holes, or handles, I should say. This is handle. This is loops. And so if you look at the number of, since this comes with the number of loops, this lambda is G squared n, is the effective coupling. So the effective coupling in this theory with only adjoints is G squared n, not G squared. And moreover, this fact also tells us something. Tells us that, so I didn't make it entirely obvious there, but you can define Feynman diagrams as being drawn on some sort of Riemann surface. So like diagrams A and B are drawn on a plane, but really we say we're drawn on a sphere. It has to be a compact surface. So diagrams A and B are called planar diagrams. They can be drawn onto a plane. But diagram C cannot. So you see one of the lines crosses over the other one. So diagram C can be thought, so if these can be thought as being drawn on a sphere, these can be thought as being drawn on a sphere with a handle, right? So diagram C is drawn on a sphere with a handle. So diagram C is non-planar and has a handle number 1. Okay? Oh, yeah. And another figure, which unfortunately it's a little bit hard to see there because I don't draw so well, but let me try nevertheless, since you cannot really see there. So if I consider an interaction of open strings that looks something like this, well, like this, I suppose, and then another interaction of open strings below it, how do I, Jesus, how do I draw this? Something like this. Anyway, I hope it's kind of clear. So these together make an interaction of closed strings. This is called a pair of pants diagram, right? It's like a pair of pants. And then this one is obtained by just cutting the pair of pants here, 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 right? Since this has to be proportional to the string, closed string coupling called GS, and the open string one has to be proportional to G open, which has to be G Young-Mills, and another G open, G Young-Mills. That means that G string goes like G open squared or G Young-Mills squared. Yeah, I actually wrote the wrong equation there. So the correct with numerical factor is 4 pi GS is G squared Young-Mills. All right. So, all right. So then, so this was the observation of 't Hooft, that you have these amplitudes in perturbation theory, and instead of in the large n limit, instead of coupling in G squared, you have effective coupling G squared n, and then these things. So you see number of handles in integers. So these are 1 over n squared corrections. So in the planar limit, I forget about this. In the planar limit, I have just coupling in terms of lambda. And now our limit is related to this, except 't Hooft was thinking as a perturbation theory in lambda, but we're in the opposite regime. We said that square root 4 pi GSN has to be fixed but large, right? So 't Hooft's limit was g squared Yang-Mills going to 0 and going to infinity, and g squared n fixed but small. Our limit is in the opposite regime. G squared Yang-Mills n is fixed but large. So this is the opposite of perturbation theory, right? So lambda much greater than 1 here. Perturbation theory was lambda much smaller than 1. Okay? So that means that our relation that we found is a duality. So let me write it here. AdS-CFT is a duality, which means strong coupling going to weak coupling, right? Because the gravitational part was perturbative. We had free gravity in an AdS-5 process 5. But the Yang-Mills part was non-perturbative, lambda much greater than 1. Okay, so that means it's useful. That means we could calculate things in a non-perturbative theory that otherwise we can't. So that's why AdS-CFT is so important. Now, this, what I wrote to you here, this was the statement at the beginning of AdS-CFT when Maldacena wrote his paper. But with the passing of times, while people started checking, making calculations on both sides of the duality whenever possible, it became clearer that we need to consider more than this limit. So when you think of AdS-CFT, there would be three possible statements. The weakest possible statement would be what I derived here. So AdS-CFT would be valid only when G string goes to 0 and GSN is fixed but large. In that case, on one side, on the string theory side, we would say we have no string correction, no quantum string correction, no string wall sheet corrections. And string theory is approximately supergravity. And then we might say that alpha prime and G string corrections might disagree. A stronger version would be to say perhaps GS still goes to 0, but lambda doesn't need to, lambda, so GSN doesn't need to be large. Maybe it could be anything. In that case, alpha prime correction would still agree, but perhaps not G string corrections. But it turns out that in the end, what seems to be the case after hundreds and hundreds of tests is the strongest version. Namely, that the duality, despite its heuristic derivation that relied at this point on these limits, it's actually true at all G string at all n, or in other words, at all string coupling and string wall sheet coupling. So that's a surprise, a very welcome surprise. All right. So what's on the board is what was in Maldacena's paper, and it's kind of a generic statement of equality of two theories, but not particularly useful in terms of calculating, because I have not given you any map between the two theories. And this map was given in two papers, one which is somewhat cryptic and so was not very clear by Gubser, Klebanov, and Polyakov. And one crystal clear that came afterwards by Witten, so that's the one that had an impact. So how do we define this map? There is, if we consider gauge invariant operators, so let me write in here, so map. So gauge invariant operators in super Yang-Mills. And these are defined by some conformal dimension and some representation in the R-symmetry group, which is either SU4 or SO6. They are the same, right? So we have this operator, and then this will be mapped to a field in AdS-5. So now the space is AdS-5 cross S5, but we have to do a Kaluza-Klein expansion on S5, and then it will give some representation of the group SO6, which is the isometry group of S5. So the Kaluza-Klein expansion is of fields is written there on page 71. So we have fields on AdS-5 with coordinate x, and spherical harmonics, so-called, the generalization of the usual spherical harmonics on the two-sphere, y of y, and they are characterized by some representation in. So then, as I said, we have OIN corresponding to phi in. And moreover, this has some dimension, and that's related to the mass. So the relation between mass and dimension is given there. D squared of 4 plus, yeah. Where r is the radius of AdS. So, as I said, in general, the anomalous dimension delta will receive quantum corrections. But in order not to have quantum corrections, we have to have special operators. And those special operators are the equivalent of these BPS states, which were special. We said BPS states are in shorter representations, and they're special. And operators are also in representations. So specifically for conformal dimensions, we're talking about chiral primary operators. Which means that there are these some combination of Q's acting on the operator gives 0. So this is like saying A 0 is 0. Annihilation operator on a vacuum gives 0. And so this tells you the operator is in a special representation, shorter representation of the supersymmetry algebra. And in that case, it cannot have quantum corrections, because if it would go into a bigger representation, which is absurd. You cannot create degrees of freedom. Yeah, I mean, you have, so I told you about the conformal algebra, right? But in the theory that we're talking about has also n = 4 supersymmetry. So we have n equal 4 super conformal algebra. Okay, so there are 4 more conditions besides the conformality condition. So the supersymmetry conditions amount to this chiral part. Okay, and I just put this funny title there because it's there in the paper of Witten, and it always amuses me. He calls it experimental evidence. So the experimental evidence for AdS-CFT was that you have the tower of multiplets of operators in n equal 4 super Mills. You can just construct. I mean, it's not really a big deal. You just count dimensions and charges, and you write all these possible operators over there. And then on the other hand, there was a paper by my advisor Peter van Nieuwenhuizen and Kim and Romans that had performed the Kaluza-Klein expansion of supergravity on the AdS-5 x S5 background. So here is a career advice that I want to give you. So the paper, Kim, Romans, van Nieuwenhuizen, before AdS-CFT had something like 3 or 4 citations. Now it has like 1,000 or 2,000 or something. So my career advice, this was an extremely good, you know, theoretical physics paper, mathematical physics paper even, right? People didn't find application for it, but eventually they did. It was a very solid piece of work. So don't, well, I mean, don't worry too much that people don't cite you if you are sure this is an excellent piece of mathematical physics. Okay. All right. So anyway, they matched. So you can see over there. There's too many things to note, but they match. So that the towers of fields match the tower of operators. Okay. So the next to consider is the AdS-CFT in global coordinates, or global AdS-CFT. So why I say this? Because the limit that we took, you might have noted, I didn't mention it, but the limit that we took us to AdS-5 in Poincaré coordinates, right? So the Poincaré patch. But that doesn't mean there's no use for the full AdS-5. On the contrary, AdS-CFT is defined for the global AdS. It's just that you need to think a little bit more when doing that. So I've written for you the, there I've written again the metric of AdS-5 x S5 in global coordinates for, in global coordinates. Well, in a particular set of global coordinates, the one with theta. There was another one with sinh and cosh, but this, I want to use this one. Because then it's easier to obtain, again, I've written that before, that the metric at the boundary is where theta goes to pi/2, cos theta goes to 0. Then you make a regularization, it's not, so cos theta is epsilon instead of 0. And then you get the metric of cylinder, infinite time tau cross an S3. And I also told you that these two possible boundaries, the boundary of the global AdS-5, R cross S3, and the boundary of the Poincaré AdS-5 cross S5, which is a plane, an R4, are related by a conformal transformation, which I've also written for you. You can find it on this page 73. Right? So now in view of AdS-5 versus n equal 4 superamyls, I reiterate that this is a conformal transformation, and therefore an invariance of the conformal field theory of n equal 4 superamyls. So whether I define the theory on one or the other is the same, which incidentally also means that is the same or whether I define string theory in Poincare or global coordinates. Although that sounds counterintuitive, because the Poincare is a patch, but it's actually the same because the boundaries are related by a conformal transformation. The only thing I have to be careful is on relating and doing correctly the map. So in the case of conformal field theory, when I do this map from between a cylinder and a plane, so the cylinder in here is R cross S3, and usually people are more used to conformal field theory in 2 dimensions, where you would consider a cylinder R cross S1, and then the plane R2, but it's exactly the same idea. When you do this transformation, you're mapping between operators and states. So let me say a little bit how that works. Yeah, so I gave the example of 2 dimensions over there. So Z equal E minus W, right? Mapping the cylinder in W, because if I change with W with 2 pi I, nothing changes in the map. To the plane, so plane in Z. When I do this, I map the following. So this map takes us between an infinite cylinder because so the imaginary part of W is periodic, but the real part can be anything, right? The real part of W can be anything. So it goes from minus infinity to plus infinity. And this is mapped to the plane where a fixed tau corresponds to a fixed radius in here. And you see, if you think of this as an infinite cylinder, you might as well think of it as an infinite line, because the radius is irrelevant. And then, what do you mean by this? Well, so this looks like a string, a state, like a state n, incoming here and propagating in this time direction. Right? On the other hand, if I define this state at tau equal minus infinity, tau equal minus, I think perhaps I should change it like this, plus W. Yeah, if I define it as tau equal minus infinity, then this corresponds to Z equals 0. So defining a state coming in at tau equal infinity amounts to something at a center of the plane. Something is what? Well, I can define an operator at the center of the plane. yeah, I did it all wrong over there. I just saw now. It's, yeah, the periodicity with z equal e to the plus w periodicity is 2 pi I, and then the incoming states at minus infinity without I. Anyway, so if I consider now closed strings in this theory, then, so now let me consider really, so this is R cross S3, R tau cross S3, and then this is R4. So I can consider, so this state would be a closed string state, right? Then I have also a mapping between states and operators. And the way this happens is the way I wrote over there. So I have a state alpha, a string, closed string state. Well, okay. Yeah, the closed string state would be with alpha and alpha tilde. All right, but except for that is the same thing. So with A daggers acting on a vacuum, that and A daggers are, roughly speaking, the you can see them in the derivatives of the, if you consider the expansion of x mu around 0, you can see them then in the dth order derivative, in the Taylor expansion. And then these correspond to the operators, which are just the derivatives of x. Okay. And then, so you have these closed string states coming in. So these are states in one dimension. As I said, the radius of the circle is irrelevant if you have an infinite cylinder. So on states in 0 plus 1 dimensions in quantum mechanics, you can act with Hamiltonians. So I can act with a Hamiltonian on these states, but then what does that correspond to? As I said, time runs radially. So if you consider this tau, then this corresponds to a radial direction on the plane. And so, more specifically, I said I d tau. This becomes like over there, I r dr. And RDR is what on the plane? RDR, if you think of this as x dx, for instance, is the same as RDR. You can see this is scaling, right? So this is a dilatation operator, the operator that multiplies every scale by a factor. Right. So if I consider 4 dimensions, as I said, the story is the same. There's only one difference, is that when I do this mapping via conformal invariance, I have to consider also possible couplings to the Ricci scalar of fields. And on the plane, the Ricci scalar is 0, right? Because this is flat. But on a cylinder, well, sorry, not on a cylinder. On a 4-dimensional cylinder, the Ricci scalar is non-trivial because the sphere is non-trivial. On the 2-dimensional cylinder, that's also plane, right? A 2-dimensional cylinder has no curvature because I can unwrap it, and it looks like just a portion of some plane. But the 4-dimensional cylinder has curvature, and so when I do this mapping, I will get some mass term here. Sorry. that's the only difference. And so here, this was so in 2 dimensions, there were derivatives of x at 0 that that were the operators corresponding to some states. But in 4 dimensions, I have different kinds of derivatives. So I have indices. And so on a scalar, for instance, I have these operators. And these correspond to Kaluza-Klein states on a cylinder. And again, the Hamiltonian, the same thing. The Hamiltonian is exactly the same thing. Hamiltonian becomes dilatation operator. So nothing changes there. All right. So now let's consider the mapping. So we've discussed the mapping of states to operators. And we also saw what happens not just in Poincare coordinates, but also in global coordinates. But now let's try to calculate specific useful quantities in the 2 theories, in the conformal field theory and in supergravity. Well, okay, so we have some supergravity fields phi, and the massless equation, box phi equal to 0, has constant solutions. And so it has constant solutions, and on the other hand, the massive equation has only non-constant solutions. So the massless has constant solutions and solutions with x0 to the power d in front, where x0 is this radial coordinate. So okay, let me write it here. So box phi equals 0. Phi goes to phi 0, and phi goes to x0, the d phi 0. And box minus m squared, so the massive ones, has only only solutions with different powers of x0. So when x0 goes to 0, which means at the boundary. And then what does this phi 0 mean? Well, it's obvious what it could mean. So this phi 0 is a source for the operator O. At least in this case, there's no doubt. The other ones we'll see afterwards. But this is a source for O. There's no doubt because the field phi just becomes this phi 0. And so what is the relation between observables? Well, so you think on the derivation of Maldacena, so it showed that 2 theories are the same. Well, if they are quantum theories, what do you say? The first thing, I mean, a posteriori, it's very obvious, of course, but initially it was not completely clear. But now you could say, well, the theory is defined by a partition function. The quantum theory is defined by a partition function. So this just says that the partition functions of the string theory in AdS must be equal to the partition function of n equal 4 super Yang-Mills. So Z in the CFT, the boundary, right? This, I have to make it as a function of a source, phi 0. And what does that mean? Well, it's a path integral with a source term, right? So, fields, path integral, E minus S plus integral O phi 0. Right? And then, so this is on the CFT side, and then on the string side. So this must also be a partition function depending on phi 0. And at least in that original limit where string theory becomes supergravity, the supergravity is the classical limit of string theory. And in the classical limit, as you know, the quantum fluctuations become irrelevant. And this is just minus S supergravity, depending on the fields. And the fields are defined by their boundary conditions. Okay? So that's what we're having here. And then the observables, so these are the partition functions, but the observables that we want are defined by derivation. Right? Just take derivatives with respect to phi 0 of Z. Then we put phi 0 to 0. Like there. Okay? And then I can substitute this Z by this Z, which is E minus S supergravity of phi 0. And I obtain a relation for the endpoint functions of gauge invariant operators in the conformal field theory as from perturbative classical calculation in supergravity. Okay, so this is a prescription. And now about some more technical details. So how do we calculate something? Well, so I can define a so-called bulk to boundary propagator. So in quantum field theory, at least the 99% of people take in their classes, you're used to momentum space calculations. But you know, you can do also X space calculations, and then you still have Feynman diagrams, just with respect to propagators in X space. And then, in particular, now, it's a particular type of Feynman diagrams that you're interested in. Feynman diagrams where you have sources, and even classical sources, at the boundary. So, one thing that you're interested in then is this bulk to boundary propagator, where one leg of the propagator is on the boundary and the other one is in the bulk. And then, as written there, you find, roughly speaking, phi of x is integral this k bulk to boundary, xy, phi 0 of y, roughly speaking, right? And so into the relation on how to calculate the correlators in terms of supergravity, I just substitute these fields. So this is phi of phi 0. This is phi of phi 0. So I substitute in here, and I just make derivations and so on, blah, blah, blah. I obtain, very easily I obtain the two-point function. In fact, for the two-point function, I actually don't need this precise relation with the bulk-to-boundary propagator. I can do it much more directly, like on the page. But in general, I need to. And here I wrote the more general relation. And although it's not needed, I said I made this two-point function calculation. Also, I made it as an expansion by using this bulk-to-boundary propagator. And you can see how that works. But you have, so this is for the two-point function, and then for three-point and higher point functions, you have to write diagrams. Now, people have been using this unfortunate name, Witten diagrams. I mean, Witten is great for having described this, but these are just Feynman diagrams. So maybe Witten-Feynman or something, or Feynman-Witten, but nevertheless. So you write these Witten diagrams or Feynman diagrams, where the only difference is these are all tree diagrams. Why there are tree diagrams? Because we're in the classical supergravity limit, so we don't have any loops. And moreover, the external points are on the boundary, right? We've seen that all of the external points containing the derivative with respect to phi 0 are on the boundary. So yeah, for the three-point function, I have this diagram. So you see here, let me say, if I have x, y, z, and then I wrote this as WW0 to emphasize this is a bulk. Point. W0 is the radial coordinate, and here is put to 0 for the boundary. So these are x, y, z, and this w are all coordinates in the field theory. So for the three-point function, there's only one such diagram. For the four-point, you already see there 3, and so on. Yeah, so I showed the result, for instance, in the case of the three-point function. So I could just look at the Feynman diagram or Witten diagram and just write the result over there, right? It's just KB from X to W, KB from Y to W, and KB from Z to W. Or, well, I call them differently, X1, X2, X3, and Z, whatever. Yeah, and then integrating over the point in the bulk, okay? So that's easy enough. Four-point function becomes much more complicated. It's I mean, the Feynman diagrams are easy, but the calculation becomes much more complicated. And so then the question is, what kind of point function, three-point functions and so on are you interested in? Well, you could consider, for instance, three-point functions of scalars, but what scalars? You have to remember that the two sides are dually related. If we're interested in perturbative calculations in supergravity, that means we have non-perturbative ones in the field theory. So, in order to be able to match something, we need some guarantee, if, well, absent any special non-perturbative techniques, we need some special guarantee that we don't have any corrections. So people have looked at at fields corresponding to chiral primaries, which we know don't have corrections, as I said. But one example that's more interesting, I think, is for a three-point function of currents. Currents also don't have quantum corrections because of being currents and being gauge invariant. So I've written there how to calculate the same idea. You take derivatives of this E minus S and put the sources to 0, just with a few more indices now. But in the action of supergravity, you have various terms. So, well, you have cubic terms and quartic terms in the Yang-Mills action, right? So you have a 3-point vertex, gluon vertex, and 4-point gluon vertex. But there's also another term when you're talking about 5-dimensional theory in AdS-5. You have also this Chern-Simons term, which has also a 4th and a 5th terms, but you're interested in one where if you take 3 derivatives, you're left with nothing else. So a 3-point a cubic interaction, and that's written over there. It's an epsilon A dA dA. And so the best thing about this is that this epsilon, because if it deals with parity, it has non-trivial parity property, which is the same as the property of the anomaly in the field theory. You could already give a general argument for the equalities of the two terms, but you could also just calculate it. So you take this Chern-Simons term, you take 3 derivatives, and you're left with 2 derivatives acting on some delta functions, right? So that should give you the 3-point function, the anomaly, more precisely the anomaly, so the anomaly of the 3-point function means d mu j mu with 2 more j's, right? So this d mu j mu should be 0 in, I mean, classically it would be 0, but quantum mechanically can be non-zero by an anomaly. So I have this d mu j mu with another j nu and j rho, right? And this is different than 0. Again, you're perhaps used to the formula in momentum space, but in X space is this. And as you also know, the anomaly is one loop in quantum field theory. So I can calculate it exactly. I don't need to do anything fancy. I know this is the diagram, and I can calculate, I get the same result. Okay. The source, right? Here I wrote phi of phi 0 for scalar fields, but now I have some 5-dimensional vectors that depend on the source at the boundary, little mu, right? Okay. Right. Yeah, so now let me consider the behavior of fields in Lorentzian space. So up to now, I've considered the things in only in Euclidean version of AdS-CFT, simply because it's much easier to consider AdS-CFT in the Euclidean case. We have seen this behavior. We also know that in the Euclidean space, we can put minus in front of the action instead of an I, and you can calculate things much more easily. In Lorentzian signature, we have things like Hamiltonians for time evolution, which are a little bit different. But before that, let me consider the propagator. The propagator in the case of so the bulk-to-bulk propagator in the case of still Euclidean space. So the propagator is found to be, the bulk-to-bulk propagator is found to be like over there. So let me even write it here a little bit. So the bulk-to-bulk propagator is g of xy, which amounts to an integral of how do I call it, like this. So this is kind of normal for the theory of Green's functions. So when you're looking for a Green's function, the propagator called in this case, you write it as the product of the two solutions, where you split. So the variable in here is x0 less and x0 more, which correspond to which of the two is greater, right? So so I have this x0 and y0, and I might call this the smallest of x0 and y0, and this is the largest, right? And then the two solutions are one with I nu and one with k nu, the Bessel functions. So one is among these two solutions, one is regular everywhere. So it means it's regular at infinity and it's regular in the center. And the other one is so this, let me call this phi 1, phi 2. So this is regular everywhere. But the second one, the second solution, is regular at infinity, but at the boundary, so x0 to 0 boundary, but in the center is blows up. Okay. And so this second solution, so let me look at this case. So this case is easier to understand. This mode phi 0 is non-normalizable, right? It's a non-normalizable mode at infinity because if I integrate it, No, I'm getting, no, x0 goes to 0. Yes, sorry. Yeah, so it's non-normalizable because if I integrate it, I get an infinity, whereas this one is normalizable. Which means the full integral is finite. And in this case, one of them is called, so I think this is called delta minus, this would be called delta plus. So we always have at infinity a normalizable mode and a non-normalizable mode. And so the phi1 is a combination of the normalizable and non-normalizable, which means itself is non-normalizable. Whereas the phi2 is just the normalizable mode at infinity, at the boundary. So it's fine at infinity, but as usual, that means that on the other side, near 0, it's not fine, blows up near the center of AdS. Okay, so this is what happened for the Euclidean theory. Now, how about the Lorentzian one? This is the more interesting part. All right. So in the case of the Poincaré coordinates, I again have so Poincaré. I again have J nu plus minus, right? Or plus minus nu. It's actually plus minus nu. I didn't remember the actual one. So, so this again corresponds to a normalizable and non-normalizable mode. And a non-normalizable. But now, unlike the case in Euclidean, where we said that one mode was sorry. So one mode blew up in the center. Now both are regular in the center. So that's new. So that means that now we have this phi plus corresponding to delta plus. That needs to be understood because this is fully regular at both sides, both in the center and at the boundary. Okay. So what does that mean? Well, it's kind of obvious a posteriori, as always, that whereas the non-normalizable mode was a source, corresponding to a source, as we saw, that was true also in Euclidean case, this one corresponds to states, right? If it's a fully normalizable mode everywhere, it should correspond to a state in the field theory. So, so the states should be mapped to a normalizable mode, and then the statement is that in this case we have phi, which is phi normalizable, plus this non-normalizable mode, which is the integral of k b del phi 0. Right? And substituting in the supergravity action, we find that so state phi n corresponded to this. So now, if I calculate the one-point function of this operator in the presence of phi 0, then I get this phi n, right? And then some two-point function times phi 0. And finally, that means that I can map the normalizable mode to sources as before, and the normalizable modes are mapped to states, we said, but another way of saying it are mapped to vacuum expectation values, right? So I said expectation values, not vacuum. Expectation values were related to phi n, okay? So the more formal statement after this is that the Hamiltonian has this CFT Hamiltonian, or the action is the same idea. But then I have this deformation by the operator with a source, alpha I, that corresponds to the non-normalizable mode. So source for non-normalizable mode. But then in here we see we also have expectation values, excuse me, in the state beta I corresponds to this beta I, which is the normalizable mode. Plus an alpha piece. So yeah. So this was called previously phi 0, and this was called previously phi n. All right, so to summarize then, we say that the normalizable modes correspond to either states in the field theory or expectation values of the operators. And the non-normalizable modes are sources. Just a moment. Yeah, all of these things I don't think I actually need are details that, no, these are details that I don't actually need. So actually, let me stop here because we're out of time anyway, and I will continue tomorrow from this point with generalizations beyond this original n equal 4 spare Mills AdS-5 cross S5 duality. So just to remind you, I said, well, let me put it here somewhere so people people remember. So tomorrow, so second lecture at 12:30 instead of 1. And Q&A at 3:15 instead of 3. Because of the colloquium of the IFT, which I had forgotten about. Anyway, so if you have questions now, ask me, and also please remember at 3, just more questions, and I'll also give you some exercises.
Can I ask a question about supergravity?
Okay.
In the first order formalism, do you have off-shell supersymmetry?
No. So indeed. So I didn't emphasize that. So let's go to the previous lecture. Right, so supergravity, so n equal 1 supergravity on this page 51 contain a graviton and a gravitino, and the theory was had n equal 1 supergravity on shell only. And the same idea as in the two-dimensional case applies. The fermions, when you go off shell, the fermions gain different number of degrees of freedom than the bosons. So you have to add some auxiliary fields. I didn't at this point. So this was just on-shell supergravity.
In general, can you have off-shell supersymmetry in a supergravity?
Sure, you have to add auxiliary fields, yes. Now the question is whether or not you know the theory with auxiliary fields. And the theory with auxiliary fields is generally known in a more simple model, n equal 1, n equal 2 supergravity, things like that. But in the more complicated models, it's generally not known.
So if I act on the spin connection with the supersymmetry generators, what fields should I expect to find?
So I didn't write it in here because, well, so I said that what we're mostly interested in is the second order or perhaps 1.5 order formalism. So the variation of the spin connection, supersymmetric variation of the spin connection is given completely by the variation of E and psi, so just by the chain rule. Now it's a complicated thing, I didn't write it, but it's given by the chain rule. Now if I consider if I consider off-shell formulations or the first order formulation, then I have to consider more auxiliary fields, and it gets complicated very easily. I mean, formulas are given, but I haven't written them.
But I guess some of the fields that are related to the spin connection are not auxiliary.
Yeah, sure. So the variation.
I am researching torsion philolography. So I have a very particular interest to understand how torsion is manifest in supergravity.
Well, so depends what you mean by torsion, but as I emphasized, the standard definition of torsion is anything that's on the right-hand side of a covariant derivative of the field bind, and that includes the fermion. So supergravity has fermionic torsion, but that's about everything in this context.
So,
okay.
Where can I read about it?
Sorry?
Where can I read about it? Where can I find the known details?
Well, yeah, I mean, okay. Yeah, there's not, there's the Van Proyen, Friedman supergravity book. There's the older review by Peter van Nieuwenhuizen, reports from 1981. Well, I'm also writing a book on that, but it will be out next year. So.
So you said the first book was what? I'm writing this down.
So yeah, there's the supergravity book by van Nieuwenhuizen. So supergravity book by Van Proyen and Friedman. There's the physics reports of Peter van Nieuwenhuizen, and that's about it that I know for sure now. So I have notes, but they're not there yet.
Thank you.